Hi everyone. This series of videos is going to take us through the beginning of the last new packet, which is covering Unit 9, and a brand new topic called logs. We're going to do the best we can in this last few weeks of school to just cover the foundations of logs, the basic ideas that you'll need to know to be successful for math analysis. So when you print out the new packet, just be advised, we're not necessarily going to do every single lesson here. We're just going to try to focus on the ones that are going to be most essential, the ones that your math analysis teachers would expect you to have a decent foundation or at least a decent understanding of, and we'll end up skipping some of the rest, which you're certainly welcome to do a little bit of self-study to teach yourself if you want to, but that of course is not an obligation. So make sure you have the new packet printed out. The first lesson that we're going to do is the one that begins on page 2, the introduction to logs. And hopefully this will give us a sense of what a log is, because I imagine right now that phrase is just kind of met with a bunch of confusion. Like, what in the world is a log? What does that do? So the first problem that I'm going to do in this first video is meant to introduce you contextually to a little bit of background information. The reason why a log exists in the first place and why it's going to solve a previously unknown problem that we were dealing with. And that's namely based on the idea behind exponential functions. You just spent the entire last chapter dealing with exponential functions. Exponential functions, some people call geometric functions, are basically anything with this structure that you see in the equation in question number 1, y equals 2 to the power of x. If you want to think of this more as a geometric style equation with an initial value of 1 and a multiplier of 2, that's also completely fine. Many people even use those words interchangeably. We call this an exponential function, but it still shares many of the same properties with a geometric sequence. So you can almost think of those two phrases as interchangeable for now. In question letter A, it wants us to complete a table. We generally know how to do that simply because we've seen enough of these problems to know that dealing with a table can be as simple as plugging in numbers into the equation, or treating this like a sequence and just using what we know about sequences, that the initial value would be 1, so there's our 0 term. The multiplier is 2, so I can multiply by 2 to get the next term, multiply by 2 to get to the term after that, and multiply by 2 to get to the term after that. So that seems pretty straightforward. We could always go backwards as well. Dividing by 2 would take us backwards through the table. So 1 divided by 2, 1/2 divided by 2, and 1/4 divided by 2 would complete the pattern. So in theory, you can complete the table however you want. All these different things are fine, because ultimately you just need to get the points that you can plot on the graph in part B. So I'll look quickly just to kind of analyze what I'm plotting. It looks like the biggest number I have to plot is 8. And I'm going to just quickly label my axes. 3, 4, 5, 6, 7, 8 tick marks in each direction. You, of course, can do this a little bit differently if you want to, and you can customize your axes a little bit, but this should give us a good foundation. All right, so plotting the points, I'll start with the nice points, and then I'll deal with the fractions afterwards. 0, 1 looks reasonably nice to plot. 1, 2 looks reasonably nice. 2, 4, and 3, 8. Hopefully you'll start to recognize this shape as that of an exponential graph. And now that you see the shape of an exponential graph, hopefully you can recognize some of its key features. Namely, the curve that gradually flattens out as we get a little bit closer to the left-hand side, which we know approaches an asymptote. That flattening out effect that we see is caused by something called an asymptote. So as I plot the remaining points, -1 and 1/2, -2 and 1/4, -3 and 1/8, hopefully you can start to kind of see the shape and say to yourself, oh, yeah, that looks right. I see that asymptote there. I can see that as the pattern keeps going, because if I did keep going backwards, I get 1/16, and 1/32, and 1/64, and 1/128, and 1/216. 215, or sorry, 256, and so on and so forth, you're just going to get closer and closer and closer to, but not actually touch the y values of 0. So that curve that we're probably used to seeing at this point is just essentially going to flatten out, not exactly touching 0, but getting really, really close to 0. And that, again, is what we call an asymptote. So this graph is an increasing exponential. It has an asymptote, hopefully clearly enough. And we know now that we can analyze that shape with familiar terminology, like increasing, stuff like that. More importantly, though, speaking of familiar terminology, let's talk about letter C. This is make an inverse table, and we haven't seen inverses in quite a while. Inverse was a topic that we saw way, way, way back in a previous chapter, and it has to do with the opposite of the table values. And in case you forgot the context for what makes something an inverse or an opposite is usually best thought of when we switch the input and the output values. In other words, we switch the x and the y values. So to make an inverse table, to indicate that all of our x's became y's and all of our y's became x's, we can actually recycle many of the points. So instead of -3 as an input and 1/8 as its output, we can keep those numbers but swap the order. 1/8 would be the input and -3 the output. Same thing goes with the next pair of numbers. 1/4 can become the input and -2 the output. Same thing with the next pair. 1/2 the input, -1 the output. And we can continue to keep this pattern going so that we can recycle all of the numbers from the table. So the inverse table is pretty straightforward. We're just switching x and y, and we'll revisit the idea of inverse again in case you're like, wait, why did we do that? You'll see inverse again in this exact same chapter. So in case you've lost that idea, don't worry, we'll have time to revisit it. But more importantly, let's visualize the inverse. Let's see if we can get a sense of what that inverse would look like. If I start to plot the points, I'll again start with nice points, and I'll do it in a different color so you can see it jump out here. 1, 0, 2, 1, 4, 2, and 8, 3 do start to form something that looks vaguely curvy, but if I do the rest of the points, 1/2 would be kind of in the middle here at -1, 1/4, -2, 1/8, -3. I'm starting to think this is giving me a very similar effect to that asymptote that I had in the previous graph, but this time the asymptote looks like it's going a slightly different way. As I make some predictions about what other x values we could have had in the table, if the table went backwards, for example, I could have had an x value of 1/16, or an x value of 1/32, or an x value of 1/64, and if I was to make a prediction, I could definitely see that these points are doing something really similar to that we saw in letter B, except it's going vertically, which we haven't seen before. So as I connect these to get a good visual here of the curve, one thing worth noting, oops, the graph went a little awry, but hopefully you can still follow it there. One thing worth noting is that this does actually look like an inverse pairing that we've seen before. If you remember the relationship between a function and its inverse from the chapter when we did inverses, I believe it was right around chapter 4, if I remember correctly, we saw that there was this line of symmetry that always seems to cut the graph directly in half when you're looking at a graph of both a function and its inverse on the same axes. I'm highlighting that line of symmetry there just to visualize it. I'll remind you that's the line y equals x. We call it the universal line of symmetry. But even then, none of that is super important right now, because what I want you to do is recognize here, we have really never seen this pink graph before. Like, we've seen things with asymptotes before, for sure, but we've never seen one where the asymptote went vertically like this. In an exponential graph, every exponential graph we made went horizontally with its asymptote. This is the first time we're seeing a graph that has a vertical asymptote. So, because we've never seen that graph before, because I wouldn't have expected you to recognize this as a graph that you've seen in a past chapter, we would say in letter E, no, there's no known function that would have given us this graph. which means this function must be new to us. We know it's the inverse of an exponential, but we've never seen it before. In the next video, we'll attempt to try to bridge the gap between this current uneasy feeling of, uh-oh, we're getting into something we've never seen before, and, okay, well, what can we figure out? Just kind of as a spoiler, the reason we haven't seen this graph before is because it's the graph of a log. And a log is a new function for us. It's the inverse of an exponential. In the next video, we're going to talk a little bit more about what a log is, and then we'll attempt to revisit the idea from number 1 so that we can get a bit more context about why a log exists.